And in the textbook, we're on page 22, very bottom page 22 is example one. Example one is asking you for the domain and range of this exponential function. An exponential function means that the input, the independent variable, is an exponent. So you could graph this. I mean, I think that would be your first inclination. But what we're asking you to do is look at this graph in terms of the pre-image. So this graph, this is the image. If we undo what's been done to the variables, we would, ready? Divide both sides by 2 and add 4 to both sides, and we would get this. So the pre-image is y equals 3 caret x. The domain and range for 3 caret x, the domain would be all reals. The range would be 0 to infinity, where 0 gets a parentheses because it's excluded. Because this graph can't possibly have a height of 0, because you can't raise 3 to any power and get a 0. If you raise 3 to the 0 power, you get a 1. If you raise it to a value higher than 1, you get a number bigger than 3. If you raise it to a number lower than 1, if you look to raise it to a power lower than 0, to a negative, you're just going to get a fraction. You're going to get a smaller value, so that if you think of this in terms of what we did in 1-2, the end behavior of this graph, the pre-image, as x goes to the left, it has a floor of 0. So now what? Well, here's the magnitude of the transformation. So if we double everything, and then we're doubling our y's. And then we are sort of doubling our range. So from 0 to infinity, double, still goes from 0 to infinity. Then we replace y with y takeaway 4, so we slid the graph down 4. So the new range, you slide this down 4. 0 plus a negative 4 is negative 4. Sliding infinity down 4 doesn't affect it. So here is the domain and range of the image. But even though you might say, well, yeah, I could do that faster without referring back to the pre-image. Yeah, you could do it faster for this question because the numbers are small. And if you get some really large numbers in some problem, and you're spinning your wheels trying to come up with an appropriate window because you've got really, really large values, it would be counterproductive. Just look in terms of the pre-image. And whatever the magnitude of the transformation is, do that to the domain and range. Okay? So that is your model. You're going to go to problem number 1. Which is on page 26. Now be careful. It's the second set of problems on page 26, where it says section 1-3 exercises. So you get one more minute and we're going to go through this. So the magnitude of the transformation, take a look at this thing, what happened? This 3, it's kind of awkward the way this is written, right? It's not, this is the older calculator key sequences, which I'm going to keep on these PDFs because most people have hand-me-down calculators. So if you have, the exponential notation on there, it'll look better than this. But this 3 really belongs at the Y. It's Y take away 3. Then you're going to undo what's been done to the variable in reverse order of operations. So you undo the addition first, you add a -3 to both sides, and then you divide both sides by -1, which is here. So the parent graph is 2 to the x. That's the magnitude of the slide. The domain, the input is not affected by, right? All the transformation got affected to the output, which is the range. So the preimage goes from 0 to infinity. And what did you do? Well, first thing you did was you multiplied the y's by -1. So that's going to change this, and it's going to open down. So it's going to go from 0 to -infinity. And then you turned around and moved the graph up 3. So it's actually going from -infinity to 0. Sorry. And when you move the graph up 3, the range of the image would be -infinity to 3. Okay. Now, moving forward, so I had this meeting with admin on Friday, and I've been thinking about this. I don't want you to be anti-busy work. So what we're going to do immediately is, as long as we can get cooperation on this, is we're going to make one of these guided practice problems the exit ticket. So as you do these problems, as you're sitting there, when I send you the Google Doc at the end of the class, you're just going to take a picture of something you've already done. So you're not going to have to go and do a different problem. That make sense? And the issue is that should minimize the busy work. Now, the only drawback to that, and why I didn't do it first last week, was if you're smarter than me, then you're just going to open the document, copy the stuff down, and tune out. Of course, that's not going to help you on May 4th. So the level of cooperation has been very high, and I'm really optimistic about all of the groups, the AP Math groups, in terms of the outputs in May. People seem to be into it. So we're going to start today, and you're going to get one of these problems that we do together as an exit ticket. Next thing, example 2. So example 2 is just something on the calculator. So just reminding you how to do this. So it's saying, right, if I look at this thing, it's 5, take away this, 2.5 caret x. So it's really y take away 5 divided by -1. There's the graph opening down. And the question asks you for the x-intercept. So that takes you to, go to problem 9. So I just want to do 9 together to make sure we remember how to do this. So you go to y equals, type that in y1, and push zoom 4. And you're going to get this picture. They want to know when the graph crosses the x-axis. So you're going to do second, trace, 0. And you have to tell the calculator, you have to surround the 0 you want, because in this case, there's only 1 0. But if you had a cubic, you had something that had more than 1 0, the calculator is asking you for more information. Now, once you do that, you get this screen at the bottom. You get this output at the bottom of the screen when you've identified the 0. So what I'm asking you to do is go second, quit, and type this. X, the independent variable key, store, the key above the on key, alpha A. Doesn't have to be A, but one of the green variable keys, and push enter. And by doing that, you won't have any issues with rounding errors, because if this were, what happened on the test last year, the AP test, was there were 2 questions, but question 1 had like A to H, and you had to use part of your answer later in the question. So you can't round this value, or you would have a rounding error later. So the issue is now you've got this number stored in A. Once you move the cursor, this number's out of X. This X value right here is just the last number that was when you traced last independent variable value the last time you traced it. So if you move this cursor, this number's gone. So by storing it in A, you're keeping that value so you wouldn't be susceptible to a rounding error. And I'm sure, I'm confident Mrs. Bratz did that with you last year, but it's been a while since you've seen it. Okay? So we're going to growth rate. So we're going to exponential growth and exponential decay. So I organize it this way, which you might think is more trouble than it's worth, but this is how we're going to do it. The growth factor is what you're multiplying the initial value by. So if X is how many time periods have gone by, 0, you have A sub 0, the amount, the initial amount, sub 0 time gone by. After 1 time period, you have that times this growth factor, how much it was growing by. After 2 time periods, you would have the term above it times the growth factor again. And then after n periods, you would have this n as an exponent, because exponents are shortcuts for multiplication. That's exponential growth. And the reason we write it that way is because if we do exponential decay, about which half-life is one example, if we're doing exponential decay, it would just be 1, subtract the rate. So we're going to example 4, which is on page 24. And it says the half-life of a substance is 20 days, and there are 5 grams present initially. When will there only be 1 gram remaining? So here's what we got here. We got this T-chart. Here's the T-chart right here. Time 0, you have 5 units. At time 1, you have the 5 units times a half, because you have half as much. But instead of writing just 1/2, I wrote 1 subtract 0.5 to contrast it with exponential growth. We don't want to be taking shortcuts. And what? From here, I worked left, and I expanded the table and did a size change of magnitude 20 to the independent variable. So it went from X to T, because they told us the length of a half-life was 20 days. 0 times 20 is 0, 1 times 20 is 20. This is your pre-image. Y is how many units you have. The initial value times 1/2 caret x. But we did a scale change of that. We expanded the x's by a factor of 20. And to do that, we do the opposite. So we go to x in the exponent and divide it by 20. So we're being perfectly consistent with the first two sections, what we did last week, and we're doing the opposite to the variable. So one way to solve the problem would be by just putting this in y1, putting 1 in y2, and see where they meet. Here's the second trace 5 down here. Except half of the AP test will be without a calculator. If we take the test that it was in the past, it is half with a calculator, half without. So if we do this problem sans a calculator, we would say, all right, y is 1. We want to get rid of, undo what's been done here. So we multiply both sides by 1/5. We divide by 5. And we get the natural log, we get 2/10 equals 5/10. 1 take away 5/10 is 5/10. That was there to prompt me. X divided by 20. So property of logarithms is I can bring this exponent out front. So that prompts me to take the natural log of both sides, which allows me to go from here to here. And then what's x? X is this over here, 20 ln 2/10 divided by ln 5/10. Well, I need a calculator to do it. Yeah, to get that answer, but perhaps they would be good with just giving you the input. Like they want to see how you got that. So just so you know, I want you to do this on the home screen. Type LOG, type clear, 20 LOG 2/10, close parentheses, open parentheses, LOG 5/10, push enter. You're going to get the same answer. It doesn't matter whether you use LOG or LN. You just can't mix and match them during the question. All right. And again, if you have a question, send me a chat and I will read the question. And if you have, you're welcome to unmute and ask the question out loud if you want to do that. But if you don't want to draw attention to yourself, that's fine too. Send me a question in the chat. So this takes you to 23. Because this is, 23 is going to be like this. 23 is on page 27. This is the question you're going to submit. So as you're writing your answer for 23, that's the problem you're going to take a picture of and return with the Google Doc. And moving forward, that's what we're going to do. We'll pick one of the guided practice problems. All right, so we're going to give you another minute, and then we're going to go over this. And if you make a mistake, submit the answer to the mistake. I mean, the point is, you can see this, but you have to allow yourself to make mistakes. That's what you're going to learn from. This cleaning up the work and pretending everything I turn is a perfect paper is counterproductive. So here's what I got. At time 0, you got 6 6/10. After one time period, you have that times a half. Except the length, it tells us in this problem, of a half-life is 14 days, sorry. So we do a size change of magnitude 14. 0 times 14 is 0. 1 times 14 is 14. So I have y equals 6 6/10 times 1/2 to the x divided by 14, because that'll expand this middle column by a factor of 14. And your t-chart would be the end columns. So it goes from 6.6 to 3.3. I want to know when it goes down to 1. So you set y equal to 1. We're dividing both sides by 6 6/10. And you end up here. You get x. Now I use common log in this problem. If you use natural log, you're going to get the same answer. It would take on the 39th day. Okay, half-life, the units are in days. So on the 39th day, you would go down to 1 unit of this. All right. Next thing, the number E. Okay. So E is a real number. It's on the number line. You will use E as much in calculus as you used pi in geometry. So I edited this over lunch. I harvested this from last year's pre-calc. And we're telling you this. Here's what you understand. Pi. Yeah, I know pi is between 3 and 4. What is it? It's pi times diameter equals circumference. So if I divide both, if I get pi by itself, I would get circumference over diameter. It's the ratio of those two. E is the limit as n gets really, really large of 1 plus 1 over n caret n. What does that mean? Well, if I put the definition of E in Y1, and I put the calculator's value of E in Y2. So Y2 is a constant. It's this line right up here. And here's Y1. And it's growing. It's approaching this line. It's not a great window, but it's good enough for now. And then here's our table. So Y2 is a constant. Then Y1 is what? Well, if I put a 1 in here, I would get 1 plus 1 over 1. I would get 2 to the first. You get a 2. If you put 2 in here, you get 1 plus 1/2. You get 3/2 squared. So you get 9/4. 9/4 is 2 1/4. So that's a quarter bigger than when the input was 1. Now what? Now it goes up by, so it went up by 1,200 10,000ths. Or go 2,500 10,000ths. Now it goes up by 1,204 10,000ths. So it's getting larger, but it's slowing down. And it's slowing down such that this number E is the limit. It's the ceiling for this. So it takes on the value of E as long as you never stop increasing the value you're adding in here and raising that exponent to. It has particular properties in calculus, but you have to understand what it is. And, you know, with the experience last year at the pre-calc group, you covered it. You just have to recall it. All right. So moving forward, the other thing is I edited the calendar, and your chapter 1 assessment, which is Monday, is no longer going to be on Khan Academy. I'm going to get some stuff together and send it to you. But that was up there as a Khan Academy assignment. I'm not comfortable with that. So that's going to be on chapter 1. You know, I'll get some stuff together from 1-1 through 1-6. You've got after school, office hours. You've got Friday to ask for clarification on something in the first 6 sections. Be prepared, but during your 48 minutes on Monday, you're going to get these assessment questions. Okay? So that's that. If anybody has a question, they're welcome to stick around. Otherwise, you're dismissed. I will send that Google Doc out, and you just see a picture of problem 23. You don't have additional work to do to be submitted. And then we'll pick up with 1-4. Now, 1-4 tomorrow, if you preview that, don't get stressed out. I'm going to deviate from the book a little bit about parametric mode, because the stuff in the book about linearization and parametrics are not on the AP test. So we're just going to try and get you comfortable with the mode itself. All right? So you're dismissed if you want to go, or if you want to stick around if you have a question. I can't tell if the wave is a question or a wave, so.
I had a question.
Sure.
I'm just.
I have a question. What's the dog's name?
Oh, Sam.
Sam. Okay. Sam boy or Sam girl?
Oh boy, he's a Bichon Poodle mix.
Okay.
I'm still a little confused on how you're writing these with like logs. I've just never seen that before. Could you explain a little more about that?
What do you mean?
Like how you're writing like log 1/6.6 equals.
Well, ready? I'm combining the steps. You're right. So if I bump up here, this thing.
And like, but like, why did you put it into log form?
Well, ready? I'm here. So if I have 1 equals 1 is how much I want to know when there's 1 left. The initial amount was 5. This is 0.5 because it's half-life to x divided by 20. Okay, so that's the question, just right here.
Mm-hmm.
Property of logarithms, one of the properties of logarithms is you can bring this exponent out front as a coefficient. So
okay, so you just do it because you want to use that property?
Correct, because if you're unknowns in the exponent, you apply that property of logarithms, and that brings you down here where your x is in a spot where you can isolate it.
Okay, so for part 1, it says express the amount of phosphorus remaining as a function of time t. Would that be like writing it as like f of x equals 6.6 parentheses 1 minus 0.5 t over 14?
Yes.
That's like part A?
Yes.
Okay, I just thought like as a function of t, you wanted to like isolate t.
Well, ready? Here's what happened. I use an x up here. X stands for number of half-lives, and t is the time. So I didn't want to confuse the issue, so I left the x in this line. Doesn't matter what letter you use.
Okay.
See, x is in terms of the number of half-lives. So here we are. 0 half-lives, 1 half-life. T is in the length. 0 times going by, 14 days is going by.
Okay. And then for B, we can just leave it as log 1 over 6.6 equals T over 14 log 0.5. That's fine.
Well, if it were a non-calculator problem, like with the calculator, you want to take this extra step because you have to, we're saying it's between 38 and 39 days. So you can't figure out you can't quantify this without a calculator.
Okay.
I just
All
brought
right.
that up saying, I only brought that up because if I said you can't count on graphing it. But
Okay.
if you had to do this, the only way you could quantify that is using the calculator.
Okay. It's just like, yeah. Like I know this stuff, it just feel like I'm getting confused because it's like in a new way, but that's it.
Yeah, well, everybody does the same thing. Like, you have Mrs. Bratz?
Yeah.
Yeah, well, everybody does that. I mean, I've had Mrs. Bratz's children for, years. And, it's helpful for you to have different teachers to see a different perspective on things, but, you'll get acclimated to this. And you're only in 11th grade. So once you get the hang of this is how we're going to do statistics next year.
Okay.
All right?
Thank you. Bye.
Sure. See you tomorrow.